Alright, so this is a tutorial for AC mesh equations, a mastery level problem in Circuit Tutor, in hopes that this will address any bugs that you could encounter on any of the other levels. So the first thing you do is a current constraint, and that's always around any given current supply. So we can look at I1S, and we see that it is moving the same direction as current I1. So all we have to do is assign current I1 to the definition of I1S, and that is our first current constraint. Then we look for another current supply, and we can see that there is a dependent supply, which is given by 2IX, and we can see that there are two meshes running through it, I5 and I3. I5 is moving the same direction as the arrow in the supply, so that is the positive current. The negative current is then I3, and we know the definition of that is 2IX, as displayed on the graphic. And then we check that equation, and it is correct. So there are no more current supplies. There is a voltage supply, however, that is not used in a current constraint equation because there's no current defined there, only voltage. So now we can move to KVL. And I like to work in the order that the meshes are labeled. The first mesh, I1, has a current supply on it. That means that you cannot do KVL around that mesh. So we move to I2, and we can see that there are two impedances on it, and both of those impedances have two currents running through them. So we pick the appropriate term for an impedance with two currents running through it. And because we're working with mesh 2, we assume that current 2 is positive. And then we just insert the impedance that it's moving across. And you can see that in inputting it, I made a mistake in the first term, but I go over and correct it right here. Yep, 2 ohms and then J4. And that is all equal to 0. So we check that equation and it checks out. Then moving over to the next mesh, I3, we can again see that there is a current supply here. This would normally be a problem, except that we can create a super mesh, unlike we could with mesh 1. So in our super mesh, there is 1, 2, 3 impedances and a voltage supply. 2 of those impedances have 2 currents running through it, so we pick the appropriate term for that. The voltage supply, again, we pick the appropriate term for that. And the last impedance only has 1 current running through it. So we pick the term with 1 current and 1 impedance, and the sum of those should be equal to 0. So again, assuming that I3 and I5 are the positive direction currents, we input all of the currents running across the impedances minus the opposite flowing current through each of those impedances respectively. You can see me inputting the information into the equations up on top. I found that the fastest way to do this is to start at the very beginning and just hit the tab button, and it brings you through all of the blanks. So we've now addressed mesh 1, 2, 3, and 5. All we're missing is 4, which is hopefully our last KVL equation. So there are 3 impedances here. 2 of them only have 1 current, and the last one has 2. And we've used all of these terms before, so this should be familiar by this point. So current 4 is running across the 5 ohm resistance. Current 4 is also running across the negative J4 impedance. And then 4 and 5 are running through the J3 impedance. And again, we assume that 4 is positive because that is the mesh that we are analyzing. So at this point, we recall that we have 5 unknowns. And it looks like we have 1, 2, 3, 4, 5 equations. That's great. So the only unknown we're missing right now is our dependent control variable. So we find where that is on our circuit, and it looks like that is shared by 2 currents. On one side you have I2, and on the other side we have I3. So we look and we see that I2 is moving in the same direction as IX. So that is the positive current in our current difference, and then the negative is I3. So we just write that IX is equal to I2 minus I3. Check equation, perfect. Now moving on to the SOT values, we are seeking a voltage and a current. We're going to start with the voltage. So if you look, we're asked for the voltage across our current supply. Ordinarily for voltage, we use Ohm's law, which would define voltage as current times resistance or impedance. However, current supplies don't have an associated resistance or impedance. So we have to look for a branch that is in parallel with this branch, because voltages across parallel branches are the same. So it looks like there is one branch, the J3 impedance, that is actually in parallel with our sought voltage. So that would mean that the voltage across this J3 impedance is the same as the voltage across the current supply. So to define our output voltage, we're going to use the information that we would have if V out appeared on our J3 impedance. So in our J3 impedance, we can see that the positive end would stay on the bottom, like is displayed for V out across the current supply, and I5 is moving into the positive account if it were on J3, which means that I4 would be negative, and that is across an impedance of J3, so V out is given by that equation. Now looking at our I out, we can see that it is in mesh 3 and mesh 3 only. And it is moving the same direction as mesh 3, so I out is given by I3. And we now have all of the equations that are asked of us in this tutorial. And since we've successfully completed the problem, we don't need to see the solution. Good luck!